So with the idea of polar coordinates, there are equations that we get that will need to be converted between them as well. One such example would be the Cartesian equations, which involve x's and y's and do not involve r's and thetas, versus polar equations that will involve r's and thetas and will not involve x's and y's. The four conversions are the same conversions that we have for converting back and forth between Cartesian and polar. Now, one big strategy that's going to be associated with all of this is, if you have just an r, what would you do with that? Typically, we want r to be the coefficient of a cosine, the coefficient of a sine, or something that happens to be squared. So in any of those cases, some algebra will be necessary. Let's talk about some examples. I would like to convert the parabola y equals x squared into polar coordinates. Now, we have conversions for both y as well as x, and those are these conversions right here. So I'm going to convert my y into an r times the sine of theta. I'm going to convert my x into r times the cosine of theta. Now there is some additional algebra that can be done here. I can square both of the factors that are on the right-hand side, so r squared cosine squared theta, and r times the sine of theta. Typically for a final answer in polar coordinates, we want it in the form r equals, if possible. So I'm going to say try to solve for r. If you have r's on both sides of the equation, it is okay to divide both sides by an r to cancel one of them out. But then I'm also going to divide both sides by the cosine squared of theta so that we can isolate one r on the right-hand side. So on the right-hand side we would have r, and on the left-hand side we would have the sine of theta divided by the cosine squared of theta. Now, one thing that frequently gets done with something like this is to talk about it in the following fashion. This would be r equals 1 over the cosine of theta times the sine of theta over the cosine of theta, which would be the secant of theta times the tangent of theta. Now, it's okay to do this. You don't absolutely have to express it in this fashion. We were done at this step. This is just to make it look a little fancier. So, on a related note, talk about converting from polar back into Cartesian. Let's consider the following example. Convert r squared times the cosine of 2 theta equals 4 to Cartesian coordinates. Now this one involves a double angle, so I'm going to apply a double angle identity to it. The double angle identity for the cosine will stick with the standard. It's the cosine squared of theta minus the sine squared of theta. This is still equal to 4. Applying the distributive property on the left-hand side, this will be r squared times the cosine squared of theta minus r squared times the sine squared of theta. That's equal to 4. And factoring out the squares, this would be r times the cosine of theta, quantity squared, minus r times the sine of theta, quantity squared, is equal to 4. Letting us know that this original equation was in fact a hyperbola. X squared minus y squared is equal to 4. Definitely not standard form for a hyperbola, but still not wrong. Let's try out one more. I would like to convert r equals cosine of theta plus sine of theta to Cartesian. Now for this case, I see that we have an r by itself, we have a cosine by itself, and we have a sine by itself. All three of those are craving the attention of one more r. Reason being, we have a conversion for r squared, we have a conversion for r times the cosine of theta, and we have a conversion for r times the sine of theta. I'm going to apply those conversions now. R squared is x squared plus y squared, r cosine theta is x, and r sine theta is y. Now, because of the existence of the x squared plus y squared, I can tell you that this thing is a circle, it's just not in standard form. If we wanted standard form, we could move the x and y over to the other side and complete the square, but honestly, I'm content leaving it as is.